All right. Let's pick up the slideshow where we left off last time. And let me make these couple of other announcements that are mostly dealing with my office hours. I wanted everybody to be able to hear this. Okay. Today, I think office hours is normal. I think on Tuesday, I was afraid I'd have to be going to the Birmingham campus sometime after 10:45 and before 12:30 to go pick up a vehicle. They let me check it out last night, so I've got the book on it. I don't have the vehicle yet, but I have the book, so I don't have to make a trip over there today. So I should be in the office 10:45 until 12:30 when my next class starts. Okay. Next is tomorrow. Most of the time on Fridays, I'm on Birmingham campus, 7:45 to 1 o'clock. I wasn't there last Friday because I had an infusion, had to be at Kirkland Clinic at 6:30 and was there until 4:30. So no way I could have been on campus last time. And then tomorrow, we're going to Opelika. Several of the math instructors are going down for our Alabama math meetings. And we'll be leaving at 6 o'clock tomorrow morning. I'll be on Birmingham West campus, but it'll be at 6 o'clock. I'll be leaving shortly thereafter and getting back about 6 o'clock tomorrow evening. So I'll be on campus twice, but you probably won't see me either time because you probably won't be there. Okay, so that's my adjusted office hours for tomorrow. Then next Friday, I can't believe this, 3 Fridays in a row, I have my annual physical, okay? And that's 8 o'clock in the morning, so I won't be going to campus at 7:45. I'll probably be at Kirkland Clinic at 7:45, but hopefully the physical will be over with in about an hour, and then maybe I'll be back on campus by 9:45 or 10. I hope. Birmingham West Campus. Okay. Any questions on anything we've covered up till now? Okay. And by the way, just for general information, we are rapidly approaching, as in next week is the end of the first mini-term. So that's our midterm, okay? And we'll be having our first test Tuesday. And hopefully everybody, I know they haven't, but everybody will have the quiz in by then. So far, I've had 3 papers turned in, which is not too bad, but out of 20 students, it should be a lot better than that. So please get your papers in, okay? You only have one more day to get February's bonus points. So if you want those, get it in by Monday. Yeah. And we won't be meeting Monday. It'll be, you'll need to get it. You can bring it, yeah, you can bring it today, tomorrow, or Monday. Yeah. Okay? All right. Number 2, the quiz. I've gotten 1, 2, 3, 4, 5, 6, 7, 8, 9 quizzes in out of 20. That means 11 people haven't turned in the quiz. That'll be fine whenever you want to. Sooner the better. So I can't return these to you till they all get in, but I will let you see what you missed on it because you need to see that before the test. And the test is Tuesday. So try to get that quiz into me, if possible, before Tuesday so I can get it graded and you can see if you were off of something. And we will have the test on Tuesday. All right. Any other questions? We were on example 6, and we had done the, actually we finished example 6, didn't we?
Yeah, but I wanted you to do the checkpoint.
To do what?
You stopped at the checkpoint.
Oh, the checkpoint. Okay, you say you want me to do the checkpoint? Is that what you said? After 6?
Yeah.
Is that f of x equals 5 minus 3x? Example 7, yeah, that's where we're going to start today. We finished example 6. We're going to start on example 7 today. Okay, now I don't think, okay, let me see. Wow. Okay. Now, had we, yeah, I think we did all this. Okay, we got all that done. I don't know why we started, why it didn't come back to this slide, but here's the deal. Example 7 isn't on the slide set. So let's back up and do it here. All right, let me get the pen activated with a dark color. All right. And it says find the inverse function of f of x is equal to the square root of 2x minus 3. Now, you might want a little timeout first. What is the implied domain here? Okay, close but not quite. All real numbers greater or equal to 0 is what this can be. But that's not the domain of x. That's what the radicand can be. So exactly what you said, but 2x minus 3 has to be greater than or equal to 0. It's what's in the radical has to be non-negative. Okay, let's solve that for x. How could we do that? Add 3 to both sides. That doesn't change anything on the direction. So that gives you 2x is greater than or equal to 3. Now what? Divide by 2. That doesn't change anything on the direction. Justin's here. Only if you're dividing or multiplying by a negative number. Dividing or multiplying by a positive number does not change the direction. Adding or subtracting, positive or negative, don't change the direction. It's only multiplying or dividing by a negative number. The 2 is positive, so that doesn't change it. All right, the 2's go out, and that gives you x greater than or equal to 3/2. That's the implied domain, so that's where we will begin, okay? Now, it's not absolutely essential for what we're doing, but it's a good thing. Now, the next thing is we've got to make sure this is what kind of function. A one-to-one function. All right, good deal. Okay, it's got to be a one-to-one function. What are your feelings on that? Yay or nay? Yay, yes, we're cheerleading for our basketball team at homecoming. Okay, now, since we know that x has to be greater than or equal to 3/2, we can actually sketch this graph pretty easily. Okay? Here's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Negative 1, 2, 3. You don't need any of those. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. Okay. Don't need all those either. Okay? But what you do know, this starts at 3/2. It's 0 there. When x is 3/2, this becomes 2 times 3/2 is 3 minus 3 is 0 is greater than 0 is 0. And then we know what our square root functions look like, right? They're basically half a parabola sleeping, okay? Shouldn't say sleeping this early in the morning. Okay, that's what it looks like. Is that a one-to-one function? Why? It's what? It's strictly increasing. Excellent answer. What's another answer you could have given? Passes the horizontal line test. Perfect. Okay? So yes, we've determined it is a one-to-one function, so it does have an inverse. What's the next step? Yes, f of x is equal to y, our primary step in everything. So y is equal to the square root of 2x minus 3. Next, exchange the x and y. This becomes x is equal to the square root of 2y minus 3. Now what? Solve for y. What's the outermost thing you got to do to get to that y? It's sort of buried here. Yeah, you got to square both sides. So when you square this side, you lose the radical, and that becomes an x squared. So we have x squared is equal to 2y minus 3. Still wanting to solve for y, what do we do now? Add 3 to both sides. And that gives us, I'm going to switch sides on it, 2y is equal to x squared plus 3, and then what? Divide by 2. Okay, so we have y is equal to 1/2 x squared plus 3. What's the next step? It's a pretty simple one. Say again? I can't hear. Yeah, change y to f inverse. That becomes f inverse of x is equal to, I'm going to write it this way, 1/2 of x squared plus 3. Okay. Now what's the next step? The one we love, right? Yes, we have to verify using our f. As you said f of f inverse. Okay, we'll do that one first. What will that be? What do we plug in? The innermost function. So that's going to be f operating on this thing here. 1/2 of x squared plus 3. What's this? Question? How you got 1/2? Well, down here it was over 2. I just factored out the 1/2 here and just left it like that. It just makes it a little easier to fiddle with. Maybe not. Maybe it's just as good not to do this. I don't know. It just seems a little easier to write. These two are the same expressions. You can either have the 1/2 out front like this or underneath there. Okay? We actually may want it back in that form. I'm guessing we might, now that I write it down that way. Let's go back and put it the other way. Not that it matters, but okay. X squared plus 3 over 2. Doesn't matter which way you write it, but let's go back with that. All right, now f has to operate on that. What does the f function tell you do? You start with the square root, and then you got 2 times whatever is in that parentheses. And that's going to be your x squared plus 3 over 2, right? And then you're going to subtract 3 from that. All right? What you reckon you're going to do first? 2 over 2 is 1, so they go away, and that gives you the square root of x squared plus 3 minus 3. Then what happens? The plus 3 minus 3 goes away. And square root of x squared is x. Ding, 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 ding. Got it. Winner. Okay. Technically, what else should we do? Do it the other way. Do f inverse of f of x. Make sure that comes up to be the identity function too. Well, what do you put in first? The innermost function, which is f inverse of the square root of 2x minus 3, right? Now, what does the f inverse? Let's use this one up here. Doesn't matter which, okay? The f inverse function takes what's inside there, which is exactly the square root of 2x minus 3, and we square it, right? Then we add 3 to that, and then we divide by 2. So which are you going to do first? Square it first, square the square root, and what does that give you? 2x minus 3 plus 3 divided by 2. Well, minus 3 plus 3 adds to 0, and 2 over 2 becomes 1, and magically we get an x, which is exactly what you needed to get. Okay? Now, I pointed out at the very beginning, x had to be greater than or equal to 3/2. What I didn't point out to you, that's the domain of f. The range of f is what? Positive real numbers greater than or equal to 0, because this is a principal square root, meaning a positive square root. Okay? So if that's going to be your domain of f, that's got to be the range, the range of f, that's got to be the domain of y, of f inverse, which is this thing, meaning we can only have positive x's, or non-negative x's, because that's what's in the range here has to be the domain there. So sure enough, now what happens to that? What's the parent function of that inverse function? This one right here. What is the parent function? X squared. How does x squared look? Okay, that's just going to be a parabola, but we're only going to take positive, so that would be like this, right? I'm not going to draw the whole thing in. But then what do we do with it? Raise it up by 3, right? Except we also shrink it by a factor of 2, so that pulls it back down to here. I can't get that to go off. Okay, so that's where we began, which makes sense there, doesn't it? And then we raise up this parabola to there, and it's something like that. And guess what, folks? Sure enough, your identity function splits those two. Here's f, here's f inverse, at least the part of it we're using, for x greater than or equal to 0. There's your plot. Now, they didn't ask you to do that, but no extra charge. Okay. Does that answer your question? Okay, good deal. That's where we're going to begin. There is a checkpoint there, which is an interesting little checkpoint, because that's a cube root function, not a cube square root, but a cube root. So I would highly recommend take a look at that, and you get if you have trouble with it, the audio video solution is at larsonprecalculus.com. This book has the best technical support, I think, of any book I've ever taught from. All right, there is a summary there, and there is vocabulary on the next page. If the composite function f of g of x and g of f of x both equal x, then the function g is the blank function of f. Inverse function of f. Very good. Number 2. The inverse function of f is denoted by, what's its symbology? F to the negative 1 of x. That doesn't mean it's a power. That just means inverse function. Okay? But it is a superscript negative 1. Number 3. The domain of f is the blank of f inverse. Range. And the blank of f inverse is the range of f. Domain of f inverse is the range of f. Very good. The graphs of f and f inverse are reflections of each other in the line y equal x, the identity function. You're absolutely right. Number 5. A function f is blank when each value of the dependent variable corresponds to exactly one value of the independent variable. 1 to 1. Excellent. And number 6, a graphical test for the existence of an inverse function of f is called the blank line test. Horizontal line test, fantastic. Okay? Homework exercises, any of the odds 7 through 11, either 13 or 15 or both if you choose, either 17 or 19 or both if you choose. Any of the odds 21 to 31, do 33, do 35, either 37 or 39 or both, either 41 or 43 or both. Any of the odds 45 to 55, any of the odds 57 to 71, quite a few there, any of the odds 73 to 81, any of the odds 83 to 87. Now those get pretty interesting looking, don't they? And then either 89 or 81 or both. And then try 93. Good practical applied problem. Then look at the exploration. There's one true false that you ought to be able to understand what that's happening. There's a graphical analysis, which is pretty good to look at. Small proof. a think about it, two think about it's that are odd, and then a one-to-one representation, 105. Don't sweat those, but take a look at those. Now, we're not going to do 1.10. That means we're through with Chapter 1. Okay? We did 1.4 through 1.9. The test will be Tuesday. Okay? Now, if you need some additional things to study for the test, you can go to the end of the chapter, which on page 104 they have a chapter summary. Now, we didn't do section 1.1, 1.2, or 1.3, but anything you don't understand there, you might want to refresh your memory on. That should have been covered in earlier courses. But anything in section 1.5 through 1.9 on pages 104 and 105, there's some good formulas and things. Remember, for the test, remember, folks, you can have a formula and equation sheet. I don't count math as being a memorization exercise. If you were working for me, okay, and I gave you a problem to do, say, hey, we need to solve this to do our project, I don't want you going by your memory. I want you looking up and making sure you got all the formulas and equations right, okay? So, okay, she was way beyond me, okay? Yeah, they were incredible. That is an incredible, and actually I didn't know they called the people computers. Yeah, and they were incredible. If you haven't seen the movie, folks, well worth the thing. Hidden Figures, incredible movie. Okay, but you can have a formula and equation sheet, bring it, okay, work it up. In fact, let me just say this as an editorial here. When I was an undergraduate at Georgia Tech, very seldom did a professor give us the opportunity of using a formula and equation sheet. In some of my upper level courses, a few of them started doing that, and then I found out how stupid I had been. Because, boy, when I had the opportunity, I went that night before and wrote down everything I thought I might need, read through, made sure, sifted through, got the important things, wrote it down, tried to remember where I had it written, went in to take the test and forgot to look at it almost. Because that exercise of writing it down, the important things, thinking through the issues, that was studying. And I never knew that, okay? I prepared better for those tests than I had those. I didn't have a formula and equation sheet. And sometimes I'd forget to look at it. Or I'd say, oh, let me just check and make sure. Yeah, that's right. Okay. So any course you're in, the night before, a couple days before, start working on a formula and equation sheet. Even if you can't use it, don't use it. Don't cheat if you're not supposed to. Okay. But that practice of doing that is one of the best study tools you can do. Okay. I'll let you use it. So work it up, bring it with you. So under review exercises on page 106, nothing there. Starting on 107, 1.4, there's a couple problems there, 43 or 45, 47, 49, 51, 53. Good review problems from 1.4. 1.5, 55, 57 or 59, 61, 63, 65, and 67. Okay, 1.6, 69, either 71 or 73. Any of the odds, oops, that's it. That's it for 1.6. Okay, 1.7, any of the odds 75 to 83. 1.8, 85, 87, and 89. And 1.9, 91, 93, 95, or 97. You don't have to do those, but if you need a little something else to practice on, good things there. The answers are in the back, and if you go back and see, use calchalk.com for tutorial help and worked out solutions to the odd numbered exercises. Okay? Then we have the chapter test. That's on page 109. Now the first few questions deal with 1.1 through 1.3, beginning at number 10. Any of those exercises, even or odd. The even answers are also in the back for the chapter test. And anything down to 23. The mathematical model, we didn't do 1.10. So anything between 10 and 23, good things to do. Now, the answers are in the back for all the problems. However, CalcCheck is still the odd number exercises. So you won't be able to use CalcCheck for the evens, but you do have the answers for the evens. Use the tools. They've given them to you free. You've already paid for them with your book. Use them. All right. Then if you're interested, doing proofs in mathematics, there's a midpoint formula that was done in 1.1 to 1.3. We didn't use it, but if you're interested in seeing how they do proofs, go for it. There's some problem solving, especially dealing, I think, with graphing calculators and stuff. So if you're interested in that, you can use those tools as well. But we're ready now to go to polynomials and rational functions, which is chapter 2. Okay? So any questions on chapter 1 before we get started? Now, by the way, chapter 2 builds on chapter 1. So what we do today is just going to reinforce what we've already done. Went to the wrong chapter. I mean, I didn't go to the right chapter. Okay, here we go. Chapter 2, PowerPoint lectures, 2.1. Okay, now there's 7 sections in 2.1. We're only going to do the first 6, 2.1 to 2.6. Now 2.1 to 2.5 all deal with polynomial functions, and 2.6 deals with rational functions. So we will pick up and go from there. Before I get started, any questions? Okay. So polynomial and rational functions. Does anyone know what we mean by polynomial? What was the prefix poly? What does that mean? Many. Okay? Now, in polynomials, many can be as few as 1. Okay? So it doesn't have to be that many. Okay? Nomial, as far as I can tell, comes from either the French or Latin or somewhere, some language that means names, many names. Well, we're not dealing with names here. What we're dealing with are terms. So basically, this means many terms, but it could be only one term and still be called a polynomial. What do we mean by a term? A term is any number and or variable that are either multiplied or divided with each other. Number multiplied or divided, variable multiplied only. Okay? That is what a polynomial is. Okay? We'll see some examples later. So what do you think a rational function is? What's the first 5 letters? What does ratio mean to you? A comparison in a division sense. So this is dividing 2 polynomials. No longer a polynomial, now a rational function. We'll get to there in 2.6. So let's not get too carried away with that. Let's start with quadratic functions. What did I say? Builds on what we've already done. We did quadratic functions in section 1.4, 1.5. In most of the thing, in fact, maybe every section, we did quadratic functions. And we'll do some modeling too. Never mind. Okay. So, what are we going to do? Our objectives here. Analyze the graph. They love graphs, don't they? Analyze the graphs of quadratic functions. We've kind of already been doing that. Now we've drawn the graphs, now we're going to analyze them. We'll write quadratic functions in standard form. Oh, I think we know that, don't we? Probably not. This is slightly different from what you're used to. And use the results to sketch graphs of functions. There's graphing again. And then finally, we'll find the minimum and maximum values of quadratic functions in real-life applications. Can't wait, can you? Okay, don't answer that question. So let's start with the graph of a quadratic function. Anyone know what it looks like? Parabola, you know it already, don't you? In this section, you'll study the graphs of polynomial functions, not just quadratic, but polynomial functions. You're introduced to the following basic functions. What do we call that one? A linear function, that one. Constant function, that one. The squaring function, which is the parent function for all quadratic functions. It's a variable function. These functions are examples of polynomial functions. Notice you can have as few as one term, and that may be just a single number is still a polynomial function. Or one term that has variables in it. And you can have exponents as long as the exponents, here's what makes a term now, the exponents now, not the coefficients. Coefficients can be any real number. Positive, negative, fraction, decimal, rational, irrational, it doesn't matter. But the exponents for a polynomial function are only positive whole numbers. 0, 1, 2, 3, 4, 5, 6. You can't have any negative exponents, x to the minus 2, not a polynomial function, not a term. Okay? That would be a rational function, not a quadratic. You can't have fractional exponent, x to the 1/2. That's like a power function. Can't have that to be a polynomial function. And anything decimal exponent, no. It's got to be whole numbers. 0, 1, 2, 3, 4, 5, 6. Okay. Your exponents. Coefficients could be anything. Okay, all real numbers. So that's what a polynomial function is. That's what a term is. Any combination of real numbers and or variables raised to whole number powers. That's what a term is. A polynomial is one or more terms. So here's a definition of a polynomial function. Let n be a non-negative, remember the exponent can't be negative, integer, can't be a decimal or fraction, non-negative integer, otherwise a whole number. Now, your coefficients, they give the symbol a. Now, the n here is just a marker. That n has no meaning. This n later will have a meaning, that's an exponent. But the subscript really doesn't mean anything, it's just an identifier. This is the coefficient that goes with the term with that as an exponent. So that they just say the coefficient of the term with n as an exponent, we'll call that a sub n. Okay? It's just some number, but it's just identifying which one it goes to. A sub n to minus 1 goes with the term where the x is raised to the n minus 1. And so on and so on. A to the 2 is where x is squared. A sub 1 is where x is to the first power, and a sub 0 is where x is to the 0. Oh, wait, what's x to the 0th power? 1. Anything to the 0th power, except 0, that isn't defined, is 1. Okay? A variable, a number, anything raises to the 0th power. So this has actually got x to the 0, but that's just 1, so we don't even write it. So this is a polynomial. Oh, wait. There's one restriction here. I said before these coefficients can be any real number. Positive, negative, fractions, decimal, rational, irrational, it doesn't matter, with one exception. A sub n cannot be 0. Why would that be? Well, if a were n was 0, a sub n was 0, that whole term would be 0, wouldn't it? Then this would be a polynomial function, but it wouldn't be degree n. Okay? It would be degree n minus 1. The degree is the maximum exponent in the problem. So we want it to be, if this is degree n, that means a sub n can't be 0. If that were 0, it would be degree n minus 1. All right, just a little picky point. So this is what a polynomial function looks like. Now, it usually doesn't have that many terms, okay, but it could. Okay. A polynomial functions are classified by degree. Okay. And the degree can be any non-negative integer. 17th degree, 3rd degree, 2nd degree, 1st degree, 0th degree, 14th degree. Okay, it doesn't matter just as long as it's a positive integer, non-negative integer. Okay? For instance, the constant function, f of x equals c, what degree is it? Second? Nope, not first, because there's no exponent to the first power. If there is an exponent, it's to the 0th power, because you don't see the exponent, right? So that's, as long as c isn't equal to 0. Now, they make that requirement, but that has degree 0. That function, what's this degree? First, yeah. If you don't see the 1, if you see a variable, but don't see an exponent, you understand it to be 1. Okay? So that's degree. degree 1. Again, if A is not 0. See, the reason C can't be 0 here, we said that leading coefficient can't be 0. So technically, that's not allowed there, and this is certainly not allowed here, because if A were 0, that would be back to being a 0-degree polynomial. In this section, we'll study the second-degree polynomial functions, which are called quadratic functions. So we've said all this about polynomial functions. We're going to restrict it to this, okay? Second degree or less, okay? So those are what a quadratic function are. For instance, you tell me, is that a quadratic function? Yes, it is, maximum exponent of 2. How about this one? Yes, it is, because if you expanded this, you'd have x squared plus 2x plus 1. The maximum exponent would be 2. Okay? How about that one?
Yeah.
Wait, what about that 1/4? That's a coefficient. It can be anything. It's the exponent that has to be good. How about this one? Can it be negative? The exponent can, the coefficient can, the exponent can. How about this? I don't see a 2 in there. But if you fold it, what would you get? X squared, and then all the rest would be less than that. So sure enough, these are all examples of quadratic functions. Note that the squaring function is a simple quadratic function, degree 2. In fact, it's the parent function of all these others. Okay, if you use that term anymore. Actually, we only use it in chapter 1. We don't talk about it much anymore, but that's still true. Okay, so the definition of a quadratic function: let A, B, and C be any real numbers. Positive, negative, fractions, decimal, rational, irrational, it doesn't matter, as long as A is not 0. Then this function would be a quadratic function. If A were 0, that would be a linear function. It wouldn't be a quadratic. So A can't be 0. But the others can be anything. Now, we've seen that before, haven't we? Where do we use that form a lot? Did it back in Math 100, I bet. Yeah, all over the place. We had something called the quadratic formula. Minus b plus or minus the square root of b squared minus a. Yeah, you know that. This was what we usually think of as our standard form for a quadratic equation. But it's not the standard form for a quadratic function. But don't worry about that yet. We're not there yet. The graph of every quadratic function, like that one, is a special type, and I really don't like the fact they call it U-shaped. I know why they say that. They say a U-shaped curve. See, a U goes straight up after a while. A parabola never goes straight up. What makes it U-shaped is that it's rounded at the bottom. That's the part is U-shaped, but it doesn't go up. It goes up, but it doesn't go straight up. It always is increasing out. That's called a parabola. Y'all already knew that. Parabolas occur in many life applications. Have you ever used a parabola? When? Second? Throwing a football follows a parabolic arc. Basketball, parabolic arc. Golf ball, parabolic arc. Everything you throw up is going to follow a parabolic arc. Have you ever actually used one? You produced one. Have you used a parabola before? Have any of you ever driven at night? Okay, what do you usually turn on? Your lights. Have you ever noticed those lights? Behind the light is a curved reflector, mirror type thing. That's a parabola. You know what's special about parabola? There's a thing called a focus. And if you have light emanating from a focus, like that's where the bulb is, the mirror behind it, it pretty much sends out all the rays in a parallel beam. No other mirror will do that for you. Only a parabolic mirror. Okay? Flashlights, those kind of things. Okay? Any of you ever use those dishes or, like outside to gather the signal? Guess what shape they are? Parabola. Because what do they have sticking up there? The receiver. Every parallel beam that comes in from those satellites way out there, okay, those come in as parallel lines, they hit that parabolic surface, and they go right to the focus. And that's why you're able to multiply your signal. Receive there, and that's why you can see the signal. What's that? Most of the time they're a little more spherical, but for, what do they call that? Astigmatism, they could be somewhat parabolic. Okay, but yeah, they could get that, but most glasses are somewhat spherical curves, and that does a focus. It's a little different. The optics of glasses are a little bit different from the mirrors, but not a whole lot. So yeah, you're right onto something. Okay, one other. See, I had something and now it flew the coop, I think. Oh, I don't know if you've ever seen what they call light farms, where they have and they had one on Georgia Tech campus when I went back to grad school. They had this hillside that had a good southern exposure and no trees around it, and they built this long situation of a parabolic mirror, and right down that, it was a long thing, so right down the middle of that, they put a pipe, ran a fluid through that, and the sun's rays focused on the black pipe and heated that water to very high temperatures, possibly enough to create steam. The idea was to generate electricity. I don't think they actually generated, they may have generated some, but they used it to heat buildings or something, things like that. It was an experiment mostly, but so they used parabolic mirrors in heat towers, or I can't think what name they give for it, but I call it mirror farms or light farms. Okay, so yeah, we use them all sorts of satellite dishes, flashlight reflectors. Your thing on a, what's that? I can't hear you, sorry. Yeah. Yeah. Okay, are you talking about a makeup mirror type thing? Oh, yeah. Okay, the outside of the car. Again, I'm guessing those are more spherical shape because you're not focusing on one point. You're just trying to give a bird's eye view. They have those in stores too. So the whole area of optics, that's a good thing in physics. So hopefully some of you will continue. Yes, do it. Okay. Now, all right. All parabolas, here's a feature of them, are symmetric with respect to a line. Now, what do we call that line? The axis of symmetry. They're symmetric about their axis of symmetry. Good, clever name. Mathematicians are creative, aren't they? Okay? Or simply the axis of the parabola. Now, how we define that? Well, also something featured in every parabola, since it's symmetric, there's some point where everything goes either up or down from, and that's called the vertex. Okay? And the line, the vertical line that goes through the vertex, whether it's going up or down, that's your axis of symmetry. Okay? The point where the axis intersects the parabola is called the vertex of the parabola, and from that point on, the parabola either goes up or it goes down. Okay? So already hinting at something we're going to do later in the section. I wish they'd have introduced it now. Now, how does this shape correspond to your function? Is there anything? Say again? Ha! That leading coefficient. Get used to it, folks. For the rest of this chapter, leading terms and leading coefficients are going to be important. Okay? The sign of the leading coefficient tells you whether this is going up or coming down. If that A is positive, that means whatever. Okay, now these other terms here, they influence some things about that parabola. Okay, but the main thing that carries forth is the leading term. That's where the exponent's the greatest. That's when your x gets large enough, that's going to dominate. Okay, and so you see any x you put in there, positive or negative, when you square it, it's going to be what? Positive. So then the sign of the A determines whether this thing's increasing or decreasing. If this A is positive, it's got to go up. If the A is negative, and this is always positive, it's got to go down. So yeah, that leading coefficient, the sign of the leading coefficient determines whether it opens upward or open downward. Leading coefficient positive, leading coefficient negative. Wow. Just from looking at the equation. Now, the A tells you something, whether it's going up or down, the sign of A anyway. Actually, the rest of the value of A tells you whether it's going up rapidly, if it's a large A, or going up slowly or down slowly if it's a small absolute value. Okay? So it does tell you something else. The B and the C, though, I'm not getting a lot from those. Okay? I can't look at that and say, oh, I know what that's doing. So B and C are sort of worthless parameters. They don't tell you enough. Okay? I'm saying that for a reason. We'll get to it later. When the leading coefficient is positive, the graph of f of x equal ax squared plus bx plus c always is going up. It's a parabola that opens upward. When the leading coefficient is negative, then the same thing, the parabola opens down. The simplest type of a quadratic function is actually x squared. The next simplest is ax squared. And then the a just tells you whether it's going up or down, but also whether it's going up rapidly, with being a tall, skinny one, or skinny one going down, or if that a is between 0 and 1, it can be a very flat parabola. Okay, it's still going up or down. It's going much more slowly. Make sense? Okay. Its graph is a parabola whose vertex, when you have that ax squared, that's nearly the simplest form, obviously the vertex is the origin. Because when x is 0, your y is 0. X is 0, the y is 0. No matter what a is, if x is 0, the y is 0. Now, if you had a b and a c out there, then that changes. But for the simplest one, okay, it's going to be going through the origin. Now, if this is curving upward, that means the origin is a minimum. Right? Nothing is any less than that. If it's curving downward, that means the origin is a maximum value. We're getting there too later. Okay? So therefore, the graph is a parabola, vertex is 0, 0. When a is positive, greater than 0, vertex is the point with a minimum y value, and it goes up from there. If a is negative, however, less than 0, vertex is the point with a maximum y value. Everything's downhill from there. All right, make sense? Okay. When sketching the graph of a parabola, the simple ones, f of x equal ax squared, it's helpful to use the graph of y is equal to x squared as a reference. Okay? We used to call that a parent function, didn't we? And then what was the a doing? If you multiply the a by something, what was that called? You multiply it by the function, so you are doing a vertical stretch, not shift. Shift would be if you did x squared plus 3 or x squared minus 2 or something. That would be a shift up or down. Multiplying by it does a stretch. Or a shrink. If the a is greater than greater than 1, it's a stretch. If it's between 0 and 1, it's a shrink. Okay? So it's helpful to think of that as a reference, and then you use your what do they call it? Transformations. Non-rigid transformation. Non-rigid transformation when you're multiplying. Okay? So here's example 1. Let's see if we can do this. Sketch the graph of each quadratic function. Compare it with the graph of y is equal to x squared. Okay? I need to get my pen darkened again. Okay? What's that? Because they know you love them. Yes, of course. They don't want to disappoint you. Okay. All right. 1, 2, 3, 4, 5, 6, 7, 8. Negative 1, 2, 3, 4, 5, 6, 7, 8. I'm not doing them very evenly, am I? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Feel like a dance instructor. 1, 2, 3. No. Okay. So let's do that parent function, y is equal f of x squared? Give me a few points. One. What value will y be then? Yeah, ordered pair. Give me an x, tell me what the y is. 1, 1, 2, 4, negative 1, 1, negative 2, 4, 3, 9, 4, 5, 6, 7, 8, 9, something like there, negative 3, 9. Okay, you've left out the easiest one. 0, 0, there we got it. There's basically kind of what our parabola looks like. What's the axis of symmetry? The y-axis. Okay, how do we name that? X equals 0. Because all along the y-axis, x equals 0. So find the x-coordinate of your vertex is 0, 0. X-coordinate 0, x equals 0. That's your vertical axis. Your axis of symmetry. All right, so there's that. Now, what we're going to do first is a good old fraction. What does a 1/3 do to you? Takes every one of those y values and takes a third of it. So what color you want this one? Second? Caroline. Oh, I should have known that. Why did I even bother to ask? Okay. So, 1/3 of 0 is 0. 1/3 of 1 is 1/3 and 1/3. 1/3 of 4 is 4/3 or 4/3. 1/3 of 9 would be 3, so that would be here or there, if I can find it right there. Okay. The next one would have been 16. 1/3 of 16 would be 16/3, which would be 5 1/3. So that would be here and here. Say again? Aren't fractions fun? Okay, yes. The answer is yes. Okay. 1/3 of 25, that would be the next one. Would be 25/3, which would be 8 1/3. That's 1, 2, 3, 4, 5, 6, 7, 8 1/3. That would be out here and over here somewhere. Okay. All right. And the next one would have been 36, and 1/3 of 36 is 12. Let's see, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Yeah, I don't have it on here. So here's what your A one looks like. Basically, it's a vertical shrink, right? The elephant sat on that first parabola and spread it out some. Okay. Now, how about G? What color you want G? Red. Okay. Here we go with red, if I can get it to X. They won't take it. There it goes. All right. The G function here, what are we doing to every value? Of your original function. So the 2 times 0 is? 2 times 1 is? 2. 2 times 1 is? 2. 2 times 4 is 8. That would be 5, 6, 7, 8. And 5, 6, 7, 8. And I don't think I'll get any more on there because 2 times 9 is 18. So this is a vertical stretch. You remember those little string toys that you pull it up and the arms go up? Yeah, never mind. That's way before your time. Okay. That would be your 3 functions. They're all 3 parabolas, all 3 at the origin. It's just different values of A. Now, what did they not include here? Yeah, they didn't include a horizontal shift, which would have been adding or subtracting something from the X. Second? Yes, nothing came down. To have it go down would have been a negative in front of here or here. Then you would have flipped maybe blue down, or flipped red down, or flipped your original one down. That's what the minus would have done. Still stretches or shrinks. All right. Any questions on that? Got to make sure I'm on staying up with the book. That was example 1. Oh, how could it be? Okay. that we are. Oh, wait. Before we go, I want you to see how they did it. Won't be quite as nice as ours, but close. Okay, there they had the original function. Then when they multiply 1/3, sure enough, that looks like it shrinks it vertically. And when they multiply by 2, it stretches it vertically. So yeah, same thing we did. And we'll start here next time. This is an example 1. Yeah, right there. Middle of page 116. Okay. Everybody, hope you know, tell your friends, the test is Tuesday. Amber wanted it Tuesday, so she's getting it Tuesday. She specifically requested it Tuesday. You get your way, don't you? Okay, so we're having the test Tuesday. Bring your formula and equation sheet so you'll be ready for the test. And graph paper if you want your own. I'll provide some if you don't bring some. Yeah, good deal. Thank you. No graph paper? Graph that.
Oh, Mr. Graph.
That's what it says.
Okay.
All right. And if you get it to me anytime today,
What are your office hours today?
10:45 until 12:30.
Okay.
Okay. Do you need graph paper?
I believe I've got it.
Okay. All right. Good deal. All right. Good deal. Any questions?